Okay, so let's do some examples of applying our new limit tests. So first of all, we will compare n cubed to n squared. So in each of the examples we're about to do, we have to decide on the ratio that we're going to use, which function will be our f function, which will be our g function. So just to be consistent, we will work from left to right. The first function we consider will be our f, and the second one will be our g. So in this case, n cubed is our f, n squared is our g. So we'll be looking at the limit as n goes to infinity of n cubed over n squared. Okay, that simplifies down to just the limit as n goes to infinity of n, which will be infinity. So if you remember from the rules we established earlier, our limit test for the ratio functions when they're equal to infinity is the definition of our little omega. So we can say that n cubed is in little omega of n squared. And if you remember, little omega is so named because it's related to big omega. So this is also known as saying that n cubed is in big omega of n squared. But of course, we can't say that n cubed is in big O of n squared. Okay, so let's move on to another example. Let's compare log of n with n. So again, we'll establish our ratio. Our f will be log of n, our g will be n. So we'll be looking at the limit as n approaches infinity of log n over n. Okay, so this one's a little bit more difficult. It isn't clear what this is, and if we recall all of our rules about limits and kind of the tables of well-known limits, it isn't exactly clear what to do with this. So let's take an aside and look at one of the tricks we can use when we encounter situations like this. So if you don't remember L'Hopital's rule, it basically establishes a way of transforming one limit of a ratio into a limit of a different ratio. So the limit of f over g as x approaches c is equivalent to the limit of f prime over g prime. So we can take the derivative of each part of our ratio. So the limit of the ratio is equal to the limit of the ratio of the derivatives. So oftentimes after taking those derivatives, we'll end up with a simpler form. So let's go back to our existing problem. And let's go ahead and apply L'Hopital's rule to try and come up with a simpler form here. So we can get an equivalent limit by taking the derivative of the numerator, log n, over the derivative of the denominator, n. And of course, that would be the limit of 1 over n over 1, which simplifies to the limit of 1 over n, which is a well-known limit. It's 0. So referring back to our rules, we've got a limit of a ratio of our two different algorithmic complexities equal to 0. So if you remember, that was actually the definition of little o. And little o is so named because of its relationship to the big O notation. So this is another way of saying that log n is in big O of n, but of course log n is not in big omega of n. Okay, let's try another example. In this case, we'll compare two polynomials, 3n squared plus 5n plus 7, and compare it with n squared. Now, based on our intuition of what we said earlier, you can probably assume that these are essentially equivalent. Remember that we drop lower order terms like the 5n plus the 7, and we also will be ignoring coefficients like 3 on the n squared. So our previous definitions kind of lead us to believe that these are equivalent. But let's go through the steps using the limit tests and confirm that in a more formal way. So again, we'll define our f function to be the first of these two, 3n squared plus 5n plus 7, and our g to be n squared. So we'll be looking at the limit of that ratio. We'll use some algebra to simplify this. So we'll divide through by the n squared, and we'll end up with the limit of 3 plus 5 over n plus 7 over n squared. Okay. Okay, and using kind of our common definitions of limits, we know that the 5 over n and the 7 over n squared will disappear as n approaches infinity. So this will end up leading to 3, our constant remaining. Okay, so if you remember our definitions from earlier, when we have a limit of f over g that leads to a constant, that's the definition of our big theta. Okay, so as we'd expect, these two can be considered to be essentially equal in terms of their complexity. Okay, let's try another one. Let's compare n to the 4th with 2 to the nth. Okay, so again, we'll define our ratio. Our f function will be n to the 4th. Our g function will be 2 to the n. So we're looking at the limit as n approaches infinity of n to the 4th over 2 to the n. Okay. So once again, we've got this problem where it isn't exactly clear where to go from here. We might have a general idea of which of these grows faster, but to be formal, we have to use some known and accepted theorems or properties. So again, we can try and use L'Hopital's rule. So let's try and apply that. So we'll take the derivative of the numerator. That's relatively straightforward. The derivative of n to the 4th is 4n cubed dn. The denominator, the derivative of 2 to the nth. Okay, so let's just do a quick review here. In case you don't remember how to find this, we've got a couple of different options. One is we could take the observation that derivatives of e to the x are pretty easy. And that we could then try and re-express this in terms of e to the x, or e, in this case, e to the n. So we could observe that 2 is just e to the power of the log of 2. Remember that e and the natural log function are complements of one another. And then we could substitute that in, and basically e to the log of 2 to the power of n. Then we could use the properties of exponents, and we could simplify that down to 2 to the n is equivalent to e to the power of log of 2 times n. And then using that, we could actually take our derivative and we could express it using e. Okay, another approach to this is we could look up some of the tables of common derivatives. So if you happen to have a calculus textbook or at a computer, you can look up common derivatives, and we would find out that taking the derivative of some constant to the power x is equivalent to that same constant to the power of x times the natural log of the constant. So in our case here, the derivative of 2 to the nth is 2 to the nth times the natural log of 2. Okay, let's plug all this back in and see how it relates to our original goal. So we're trying to find the limit of n to the 4th over 2 to the n as n approaches infinity. That'll be equivalent to the limit of the derivatives of n to the 4th over the derivative of 2 to the n. Oh gosh, so that leads us to kind of a messy formula, 4n cubed over 2 to the n times natural log of 2. So it doesn't seem like that got us very far, but we could continue to apply L'Hopital's rule and see if we can get this to be any simpler. In fact, if we repeatedly apply it, as we can see, the numerator, the exponent on n, will continue going down. So let's continue applying it. So we'll apply it again and again and one more time. And at this point, we have completely eliminated the variable in our numerator. So we now are trying to find the limit of 24 divided by 2 to the nth times natural log of 2 to the power of 4. Okay, so at this point we've got a constant being divided by some exponential 2 to the nth. And again, we could look up in our commonly accepted limits, and we would observe that the denominator keeps growing and the numerator at this point is fixed. So the limit of this will be 0. And going back to the definitions in our various limit tests, if we have a limit that's 0, we found a little o. So in this case, we can say that n to the 4th is in little o of 2 to the n. And again, that's related to the big O notation. So n to the 4th is in big O of 2 to the n. So it's bounded above by 2 to the n, but it's not bounded below by 2 to the n. So it's not in the big omega. Okay, so generalizing, we can actually show inductively that for any real values, a, which is greater than 1, and b, which is greater than or equal to 0, that some n to the power of b. So basically what we're saying here is that we've got polynomial, and we're comparing it to an exponential. Okay, so exponentials, the thing on the right, always grow faster than polynomials.